Hello everyone, it's me, Professor Aaron Albert, here again with Lesson 32. Let's learn some econ. So we're going to keep going with game theory, and today we're going to move on from static games to dynamic games. And we're going to show you how to solve for Nash equilibrium in a dynamic game using a technique that is known as backwards induction. So in a dynamic game, the only difference is that people make choices in sequence. That is, player 1 chooses, then player 2 chooses. And then perhaps player 1 chooses again, and then maybe player 2 chooses again. And these keep going in sort of a tree-like pattern until the game is resolved. In dynamic games, we either have players choose to move sequentially or repeatedly. That is, in a dynamic game, we could have player 1 and 2 choose at the same time, and then have them choose at the same time again, then have them choose one after another, right? Any mixture of sequential and repeated moves, as long as there is more than one time that people are making choices, we have a dynamic game. Also, we will assume that players have complete information about the payoff functions. That is, both players know their own payoffs and the other player's payoffs for all outcomes. Also, at any point in time in the game, both players we will assume know everything that has been done up to that point. And this is important to remember that, again, there is a subtle difference between action and strategy. Action is a move that a player makes at a specific point. So if we have several decision times, an individual could have to make a bunch of actions. The strategy is what we call a battle plan. It just describes what action each player will make at every single point that they have a decision that they could make. And this is important because the way the game works out, there might be decision moments that are not encountered. You still need to, in order to define a strategy, say what would have happened at that point. Let's assume that you're playing, for instance, rock, paper, scissors, where the first person plays rock, paper, or scissors, and the second player chooses rock, paper, scissors in each case. It might be that you know you're going to go this way and that the other person's going to go this way. It might be that only this path matters, but you still should know what to do at these other nodes that have not been named. So make sure in tests, in quizzes, and in your life, anytime you define a quote-unquote strategy for a dynamic game, you completely specify what's going on off path. Alright, so this is a finite dynamic game. In this, we will say that American Airlines chooses either 48, 64, or 96 flights per day. United observes this, and then they choose 48, 64, or 96 flights in each of these three cases. So, take a minute and see if you can define for us what an action is for both United and for American, and what a strategy might be for both American and for United, using the definitions we just went over. Go! Alright, the actions for American appear to be, they only have one decision node, it's here. They can either choose 48, 64, or 96. United has three action nodes, 1, 2, and 3. And on each one, it looks like they can choose 48, 64, and 96. So it looks like actions for both players include 48, 64, 96. Next, strategy. A strategy for American is, I will play 48. I will play 64. Or I will play 36. Strategies, however, for United are slightly more complicated because United has to make a decision at each of these 3 points. So if you were to say United plays 48, that isn't necessarily a strategy because you haven't told me when, where, how, why. Strategies for United include always, and then you could say 48, 64, or 96. Or you could say they do 48 if top, followed by 64 if middle, followed by 96. Or they could do 48, 48, 64, or 48, 48, 96. you can see that the set of strategies United might want to play is a very large object. So again, just to be painfully clear, make sure when you're defining a strategy that you name the action for each player at each node. American chooses one, only need to give one action. For United, you must tell me 3 different things that they're doing, even if they don't get to some of these actions. All right. How do you solve these? Well, you'll note that player 2 has their payoffs listed second, i.e. United, and player 1 has their payoffs listed first. What we need to do first is circle the biggest payoff for the second player, since United goes second, and they are choosing. We're saying if United ever found themselves at this node, they would choose the best option for them. So we know that if United observed 48, they would choose 64. Similarly, if United observed 64, they would choose 64. And if United ever observed 96, they would choose 48. All right. So we know that these are the 3 choices that would be made by United. This is United's strategy. They would choose they would choose 64, 64, and 48, which yield them payoffs 5-1 if 64, 4-1 if 64, and 2-3 if 48. Next, we're going to assume that American is pretty smart. They're going to observe that United would do this, and they're going to choose what's best for them. Would United like 3-8, 4-1, or 4-6? Well, it looks like American would really prefer the 4-6, so we know that American is going to choose 96. After American has chosen 96, United will observe 96 and choose 48. So the actions that we will observe after this game has been played is American plays 96, United plays 48. However, that is not the strategy. The strategy would be American plays 96, United plays, and I'm just going to read them from top to bottom, they'd play 48 implies 64, i.e. if they observe 48, play 64. If they observe 64, then they play 64, and if they observe 96, they will play 48. Or we could have just listed it shorthand. I could have gone like, oh, United is going to play 64, 64, 48. And this is assumed that I'm just going top to bottom. But either way, you'll note that this means United's making 3 choices, not just one. All right. The important thing to note is that this is a Nash equilibrium. Now let's prove it. I'm going to then just, again, highlight the choices made. The only choice United can have that really matters is what they do here. And does United want to deviate to 64? No. Do they want to deviate to 96? No. So that means there'll be no deviation here. Next, if United unilaterally decides to deviate here or here, it doesn't matter since those nodes are never reached, right? Those are what we call off path. Next, we'll move to American. Does American have any incentive to deviate? Well, if American deviated to 64, they'd get 41 utils, which is worse for them. If they deviated to 48, they'd get 3.8 utils, which is worse for them. Therefore, we can say that this is a Nash equilibrium. The strategy we just applied, the solution method we just applied, is called backwards induction. If you go towards the end of the tree and you pick the best choices all along the tree for the second player, and then choose what the first player would do, knowing the second player will do that, you will find Nash equilibrium every time. And in fact, you will find what's called the subgame perfect Nash equilibrium. Basically, we will show you in a minute that there are often many Nash equilibriums in these games, but only one of them will be subgame perfect. Subgame perfect means everybody is doing the right thing at every single node. There's only going to be one backwards induction solution, but there will always be one. So when you're solving these games, observe the tree. First thing, find the SPNE, the sub-game perfect Nash equilibrium. You get that through backwards induction. And then see if there's any other Nash equilibriums. And we'll get into that next. All right, so one caution, finding the other Nash equilibriums can get a bit complicated. Basically, the other Nash equilibriums, what we're going to do is we're going to wiggle some of the choices and see if we can find something that's stable. Basically, this always is done by trying to find a bluff. One bluff we can try is player 2 doing 64, 96, 96. If player 2 does 64, 96, 96, what will player 1 do? Well, player 1 observes the best that they can get is this 3.8, so they will play 4.8. Now let's check that's stable. Player 1 does not want to get 2-0 or 0-0, so they will indeed choose 4.8. Next, if player 1 has chosen 48, will player 2 want to deviate from 64? Looks like no, this 5-1 is pretty juicy. Therefore, this is a Nash equilibrium. We don't say that this is sub-game perfect Nash equilibrium because player 2 is not doing the right thing in all of the sub-games. For instance, imagine that American Airlines sneezed, hit the wrong button, and ended up playing 64. If they ended up playing 64, and then United played 96, well, United wouldn't play 96. They'd say, oh, whoops, I was just kidding. I meant to play 64. So the only reason United has convinced American to play 48 is because they've bluffed. They've said, hey, American, I'm going to play 96 unless you play 48. So American says, oh, well, back's against the wall. I better play 48. And if American believes United, United gets a very juicy payoff. They get this 5-1. But we say it's a bluff because if we ever ended up at these other two nodes, United was bluffing. They would not play 96 in either of these two cases. Because United was bluffing in this 64, 96, 96 equilibrium, we say that it's less credible, right? It is not a sub-game perfect Nash equilibrium. All right, here's another game. Go through this one, see if you can find the SPNE. And then, if you get bored, tell me if you can find another non-SPNE solution. All right, let's look for an SPNE. The entrant, going second, will be the first thing we decide. It looks to me like 4 is greater than 0, and 0 is greater than -1. So they would choose this, and they would choose this. Player 1 observes that they will either get 4 or 8, and they prefer to get 8. Therefore, the sub-game perfect Nash equilibrium is one in which player 1 plays invest, and player 2 plays enter if and no invest, do not enter if invest. The resulting actions are invest followed by do not enter, and the resulting payoffs are 8, 0. Pretty easy. Next, are there any other Nash equilibrium? Well, I wonder if there's some way, you'll note in the way we did it before, that player 2 ended up getting 0. I wonder if there's any way we could convince player 1 to allow player 2 to get 4-4. So let's say they do this here, and then they tell player 1, hey, I'm going to enter no matter what. So if player 1 hears that player 2 is going to enter no matter what will they do? Well, the choice is between 4 and 2. It looks like they will not invest. Let's see if this is an equilibrium. Player 1 chooses no investment. Player 2 enters. They get 4. Player 2 doesn't want to deviate since 0 is worse than 4. Next, moving to player 1, they choose either between this 4 or this 2. They'd prefer the 4. So this indeed is an equilibrium. However, this player 2 claims they're always going to enter, and then player 1 is unhappy and chooses not to invest, is not subgame perfect. Why? Because it has a bluff. Player 2 is not going to enter if player 1 invests, right? They would -1 themselves. That's not a thing that they're going to do. So that's why we think these other Nash equilibriums are a little less believable, but still interesting to find. All right, here's one more. Take this game, draw it as a tree in which player 1 goes first and player 2 goes second, and see if you can find the subgame perfect Nash equilibrium. And then repeat it with player 2 going first. Go. All right, let's try it the first way. Looks like we got 4 forks. Sound effects really help. They help me get my game theory in. All right, and who went first? Player 1 went first. Player 1 chooses up or down. Player 2 chooses left or right. Left or right. Now the only trick is transposing these numbers correctly. Up left gives me 1, 1. Up right gives me 2.5. And 6. Down left gives me 2 and 0. Down right gives me 3, 3. Alrighty. Does player 2 want 1 or 6? Looks like they want 6. Does player 2 want 0 or 3? Looks like they want 3. Next, does player 1 want 2.5 or 3? Looks like they want 3. Therefore, the solution we observe will be the actions player 1 plays down, player 2 plays right, and the strategy is player 1 plays down, player 2 plays right, right. In order to save myself some time and energy, I'm not going to reverse the game, but trust me, it's the same process. It's not very hard. The reason game theory is interesting is because sometimes we get surprising findings. For instance, there is such thing as an ultimatum game in which people take it or leave it offers and they give each other very low amounts. We can talk about that in recitation if you remind me, but for simplicity, let's just talk about the centipede game. It's very centipede-y. In the centipede game, player 1 and player 2 take turns making down or right offers. I.e., at the beginning of the game, player 1 says either we go down and I get 1, you get nothing, or we go right. Then player 2 says the same thing, down or right. Then player 1 says the same thing, down or right. And player 2 says the same thing, down or right. And the important thing is, if they keep playing right, they get this juicy 3-3 payoff. If they instead cheat and they go down, they result in a 1-0 payoff. So let's see what they do. Player 2 chooses between 3 and 4. They will choose 4. Player 1 then chooses between 2 and 3. They choose 3. Player 2 chooses between 1 and 2. They choose 1. Player 1 chooses between 1 and 0. They play 1. Therefore, the solution to the centipede game is they both get very little, and it's very unsatisfying because there was this juicy 3-3 over here on the right. So, the conclusion is, these dynamic games are fairly easy to solve as far as getting the SPNE. All we need to do is just do some backwards induction. However, in these games, finding the other Nash equilibriums can be a little tricky. Thanks so much. See you next time.